So today we're going to continue with the choice under uncertainty. And so we need to introduce right now this independence axiom, which is the special property that expected utility satisfies on top of being rational. Okay. So I said last class that you have to play three lotteries, P, Q, and R. And then the independence axiom requires that if I observe in an experiment that this decision maker chooses P over Q, then this implies that if the same decision maker is given a compound lottery of P with R with a mixture parameter alpha and another mixture of Q with R with the same mixture parameter, then this decision maker will still choose the compound lottery PR with the compound over the compound lottery QR. So this works for any triple. So in particular, this axiom is very strong because this is telling you that you have this independence between the different probabilities. So this is the perfect substitutes property, V1. So everyone understands the axiom. So we're going to try to understand it a little bit later, but this, as you can imagine, this is implied by the expected utility model. So again, so what is the expected utility model? Is this model where you take the value of the lottery is equal to the summation over the probabilities of each state of the world multiplied by the Bernoulli utility, okay? Which is this weight given to the particular money price you get in each state of the world. And in particular, if you are expected utility maximizer, then you're going to satisfy the independence property, okay? Now, examples like the Cobb-Douglas that I created here, these are non-expected utility, right? In particular, this fails the independence axiom. So if you mix with an R, so imagine V, C, D of P is greater than or equal than B of Q. So what happens? If I mix it alpha P with R, what will happen with this utility? You have here P plus R1 to the alpha, P2 plus R2 to the 1 minus alpha, right? So that's not, that doesn't have to be greater than or equal than Q1 plus R1 alpha and so on, right? So this only works whenever you have expected utility because of the linearity and additivity, you're going to get that P1 plus alpha P1 plus alpha R1 multiplied by U, and you do the same for each entry, P2 times alpha plus alpha R2 and so on. And then when you compare it with the utility of Q, right, you're going to get the same thing because the additional term with R is going to get eliminated when you subtract UP minus UQ. This is the same as doing U alpha P plus 1 minus alpha R compared to U of alpha Q plus 1 minus alpha of R. Okay, so this independence axiom is basically an implication of expected utility. Now, it turns out that we're going to show that essentially this property with rationality implies that you are expected utility as well. Okay, so it goes both ways. Okay, so independence is basically the whole content plus transitivity and completeness. And you also have here a technical property, which is called mixture continuity. So mixture continuity is similar to the continuity property we require in the chapter 3, but here we need to impose this continuity for the space of lotteries, right? So in particular, imagine you have 3 lotteries, and then you have that P is better than Q and Q is better than R. Then if you take all combinations of alpha P plus 1 minus alpha R for all alphas, and you do the same for all combinations alpha P plus 1 minus alpha R that are worse than Q. So the upper contour set and the lower contour set strict combinations with alpha. Both sets, which are subsets of the space 0, 1, are open. So in this mixture continuity property is very technical, but it's gonna ensure that the Bernoulli utility is continuous, okay? So this is gonna be the role of it. In particular, you can see the independence condition as the behavioral condition that we can test, and the mixture continuity as a mathematical property we need to in order to make it equivalent, transitivity and independence with the existence of expected utility. And this continuity is the same role as the continuity for the representation of utility. In chapter 3, if you don't have a continuity, then there are some issues in the mathematical representation, right? So I'm going to tell you the result, and we're going to prove it this class. So the preference relation that satisfies, preference relation satisfies independence axiom. So we have to actually say that this is actually a rational preference relation. Satisfies the independence axiom and mixture continuity, even only if there exists a small utility, Bernoulli utility. So let's qualify it as well here, Bernoulli utility function U, going from Z to R such that P is greater than Q, and the expected utility of P is greater than or equal than the expected utility of Q. Okay? So this is a utility representation that is way more precise than the chapter 3, right? Because at this level, we are providing a expected utility representation. So it's not longer transitive and complete, it's also independent. And because of that, you get this additive structure, which is almost perfect substitutes, okay? Everyone understand what I'm doing here? So what I basically claim is that the ranking, the binary relation, if satisfies independence and mixture continuity on top of being rational, then you can actually construct expected utility representation of the binary relation. And if you have expected utility representation, right, then if you construct a binary relation on the basis of this utility, you will get something that satisfies independence and mixture continuity, okay? So the first part is you take this preference relation that is rational, and we're going to show that the independence axiom and mixture continuity implies that there is a linear function U that goes from the space of lotteries to the reals that represents the preference. So notice here that we are just in the lemma before the full proof is that we are showing that independence basically is going to give us that the whatever utility there is on this space of alternatives will have to be linear. So this is from math. So can Heng Fan tell us what is a linear mapping? So what? So a linear function is equivalent to what properties?
Independence axiom.
No. Like mathematically. So you have a linear mapping. So when do you say a mapping is linear?
From the Bernoulli utility function, the sum of the Bernoulli utility function and P.
Yeah. So you take you have the linear mapping, and you apply it to the sum of, for instance, lottery P plus Q is going to be equal to the function evaluated at P plus the function evaluated at Q, right? So that's basically it. You also have to that the zero unit goes to zero, right? Else is a fine. Yeah, someone was saying something.
Yeah, so does the function also have to be one to one?
So right now we're just proving one side. So this is that. So we don't require that right now. We're just proving that if the binary relation satisfies independence, then the utility that represents such preference relation has to be linear. Okay, nothing else. We're not showing onto um, injectivity. So okay, so what I'm gonna do here is a very constructive proof, as opposed to the proof that I did in chapter 3. So this proof is simpler in a way. And actually, you can imagine the experiment that someone is running. Okay, so the first part is that we're going to find two lotteries inside this choice set. And we're going to choose it such that R1 is above P and R2 is below P for a fixed lottery P. Now, so to ensure that these objects exist, we use continuity, okay, and final method of set. So the second step is to define a candidate utility function, okay? So the candidate utility function is going to be P, such that according to the preference relation, which is my information, is indifferent to the mixture or compound lottery, or according to mixture parameter alpha P, from R1 and R2. So notice what is the trick here, right? So first, I use my experiment to find a lottery that is always better than P, and then I find another lottery R2 that is worse than P. And then I find the compound parameter of the lottery, so this alpha parameter, right? That will give me a new lottery that the subject declares to be indifferent to P. And then I'm going to assign, and this is a candidate utility function, as the number that represents the binary preference, U of P is equal to alpha P. Okay, so this step is as usual, the step where the proof has some spark, right? So this is not algorithmic. This is the creation of the person that did this proof, right? So von Neumann, Morgenstern. So we are proposing this mixture parameter as the utility number, okay? And then we're going to show that this function that I created is linear. So, so the objective is use independence to show linearity of the proposed function. So this is what I'm going to do next. So if P is strictly better than Q and alpha is inside 0, 1, then notice that I can take P and take a combination of alpha. I'm gonna claim that P is strictly above alpha P plus 1 minus alpha Q, and this is above Q, right? So this follows from the dependence axiom. Know that if we have P better than Q, then we combine it with the third lottery, in this case Q. Notice that the right-hand side just becomes Q, right? So that means that this mixture is better than Q. So the second two parts of the triple condition. And the same thing goes for the first part, right? And now I get this kind of sandwich property. And now by transitivity, I have also that P is better than alpha P plus 1 minus alpha Q better than Q, okay? So this is just an observation that if I take two lotteries, such that P is better than Q, I take a mixture according to an alpha that is not extreme, it's not in 0, it's not in 1, I get an object that is in between, right? In terms of preferences. Everyone understands? Okay. So now I'm going to do a more generic construction for any lottery. And the way I'm going to do it is, again, take a lottery that is better than the lottery of interest P and take a lottery that is worse. Now, the key is that I'm going to do, I'm going to choose two lotteries that are always the same for every lottery. These are going to be the best lottery P plus and the worst lottery P minus. So these are best in terms of the best possible lottery in this set. So in particular, the best lottery, usually, so we know it exists because we know that we have the generate lotteries. So take the space of monetary outcome, Z, and imagine, the highest monetary outcome that this space gives you. So imagine my monetary outcomes are 0, 1, 2, 3, so, until $10, okay? So then the best lottery is going to be the lottery that gives you with probability 1, $10, okay? So this is P plus. And what is going to be P minus is going to be 0 with probability 1, okay? So P plus, P minus are the best lottery and the worst lottery. So does this, do these lotteries exist always for any set? So what do you think, Nico?
If this, I would say yes, if the set satisfies transitivity and it's not like there's no cycle?
Well, so remember the preferences were stabbing and transitive and complete, right? So we know these preferences are transitive and complete, and the space of the choice set is just a space of lotteries. So the space of lotteries is a simplex, right, which happens to be closed and bounded. So because lotteries are Euclidean, they live in a Euclidean space. This is a compact space. So you're maximizing a transitive and complete preference relation on a compact space. So you always have a maximum, right? And by the same argument, you always have a minimum. So yeah, your answer was roughly correct, but the exact words were a bit vague. Okay, so everyone understands what I said? So because of transitivity and because of completeness, I can always assure that there is the P plus and the P minus. Do you agree? Okay. So again, so these two lotteries exist because the preference relation is transitive and complete, and the simplex is a compact set. Okay. Now I'm going to do it constructively. So take alpha and beta in 0, 1, and I'm gonna just make the following observation, which basically means that my proposed utility is actually representing the preferences. So this is the representation part of the theorem. So this is telling me that if I take, so remember, take beta greater than alpha, and now observe that if I take the combination of P plus, P minus with beta, and then I do the compound lottery with alpha, P plus, P minus, then it has to be that this compound lottery is strictly better than the other compound lottery with alpha, okay? So beta is giving higher weight to the best lottery, right? And alpha is giving, is slightly relative weight higher to the worst lottery, okay? So this is the representation part, okay? So this is obvious from this construction, right? So I'm just taking a combination of something that is better and then comparing to something that has a little bit more weight on the worst outcome. So this is telling me that pretty much the preferences that I'm getting are a representation of the binary preference relation. So the alpha, this alpha p that I'm going to construct in a second is going to be a utility function. So let's do that. So take any lottery p, and there is a unique alpha p such that the compound lottery p plus p minus according to alpha p is indifferent to p. So why this is unique? Well, existence, first of all, has to exist. It is a consequence of mixture continuity, right? So now note that I have a p plus is weakly better than p, and p is weakly better than p minus. Then this set here, which is a little bit different from the definition of mixture continuity, because this contains indifference, right? That this is the upper contour set V1, and this is the lower contour set. Because this includes indifference as opposed to the definition, this is closed. So this is the closure of these open sets in the definition. So then there is a sequence of alpha n's in the intersection of both sets, right? Such that they converge to alpha p, okay? So we know that a bounded sequence in a closed interval converges to alpha p exists and is between 0 and 1. So uniqueness comes due to step 2. Okay, so step 2 is again the representation theorem. So imagine the alpha is not unique. So because alpha is a real number, it means that if there is two alphas, alpha and alpha prime, right? There are two possible cases, and in fact, one without loss of generality. Alpha is strictly greater than alpha prime. If that happens, then it has to be, right, that this combination or compound lottery with respect to alpha is strictly better than the combination with respect to alpha prime. So because of that, then they cannot both be indifferent at the same time to P, okay? So uniqueness follows from step 2, which is this obvious observation, and existence comes due to continuity that allows you basically to this sequence to have a limit, okay? So basically we know it converges to some point. Now we know there is only one point of convergence, okay? So this accumulation point or original, and then we get actually a convergence and a limit. So now comes the proof, so the final part of the proof. The utility of P, therefore, is constructed as alpha P, as defined as this mixture that gives you the indifference. With a P plus P minus, according to the mixture alpha P, gives you indifference to P. So at this stage, I just want you to visualize what's going on with an experiment, and then we're going to finish the proof, which is rather easy. But the final part that we need to do is show linearity. That's the only part of the result that I'm missing. But right now, I just want to visualize that this is actually something you can do in an experiment. So, okay. So let's go back to my experiment. So I found that the best lottery is $10 with probability 1, and the worst lottery is $0 with probability 1. Now imagine I want to see understand the utility, right? What is the value that the subject, the decision maker, the experimental subject gives to a lottery that gives you 1/2 to $10 and 1/2 to $0. Okay. So how I can figure out the value? So one way to do it is the following, right? So I say, okay, I'm going to assign and normalize the utility of the best lottery to 1. So the maximum possible utility number here is going to be 1. And the worst lottery is going to be 0. Okay, I normalize the values of the utility. So now any utility number for any P is going to be between 0 and 1. Got it? Now, so what kind of experiment can I run in order to figure out what is the utility you assign to P with this 1/2 10, 1/2 0? Well, an easy experiment would be to follow a list, right? When I'm telling you, look, with probability 90%, alpha equal to 90.9, you get $10. With probability, the remaining probability, 0.10, right, you get 0. And then I run a different one when say 0.8, 0.20, 0.7, 0.20, right, and so on. And then this guy eventually, so is gonna, and then this is the constructed lottery, right? So this goes running in the first column of my experiment. And then in the second column, I always offer this guy the lottery P, which gives you probability 50% to 10, 50% to 0. So I run this thing, and then the subject is gonna tell me, I like the 90% $10, of course, right? Then I like the 80% and so on. And then eventually, right, at some point, the agent is gonna flip, right? So it's gonna switch to the other one. So now you know in between these rows is the true value of the utility, right? So and this of course is going to correspond to the alpha P is gonna be the utility number. So whenever, say this guy, for instance, flip exactly at 50%, right? So this is this is a guy with the utility is the identity. So you found out that the utility is actually 0.5, okay? So you can run these experiments and you can eventually find the number that makes you indifferent between the lottery and this P plus and P minus. And because you cannot run every possible number, right? You can actually do this sign of lists and then basically see the flip when the consumer goes from choosing the first column to the second, right? And then when that flips happen, it bounds the utility, right? Now we assume, of course, that we have an infinite experiment, so we can figure out exactly alpha P. So everyone understands how I get alpha P. So this alpha P, now also notice, is a cardinal value utility, okay? So this is actually intensity of how much you like utility, the utility, how much you like this lottery, okay? Between 0 and 1. So now I want to show the final part of the proof. The objective of this theorem is to show that this utility is actually a linear mapping. So linearity means that if I apply this utility to the weighted sum of P and Q according to the weight beta, I also get that this is equal to the sum of the utilities, right? So beta times U of P plus 1 minus beta U of Q. This is linearity, the part I care. And then note that by definition, P is indifferent to the mixture parameter UP of P plus 1 minus UP of P minus. Notice here we just do a change in notation, right? By step 5, we know this is equivalent. So we just replace the alpha P by the UP. Agree? Okay. So I do the same for Q. And of course, this has a different mixing parameter, U of Q. And now I have to show that if I take now the compound lottery, beta of beta times p plus 1 minus beta of q, then the mixture parameter that I need in order to make indifferent the p plus and the p minus is actually equivalent to this object here, which is beta plus 1 minus beta, okay, of the utility that I have. So this will prove linearity, in other words. So notice that I just take p, right? And this lottery is indifferent to what? By definition, is indifferent to up, p plus, 1 minus up, p minus, okay? And then q, I just leave it as is. Now, q is indifferent in its own time, right? To uq, p plus, 1 minus uq, p plus, p minus. So now I get beta, parentheses, the lottery, which is a compound lottery that is indifferent to p, and 1 minus beta, the compound lottery that is indifferent to q. Now, notice that these objects now, they are just operations in the space of vectors. So I rearrange terms and basically take beta and multiply inside. So remember, now these are just vectors. And I get now beta up plus 1 minus beta uq, right? Rearranging. So I'm taking this, breaking it up, taking common factor p plus, and then I do the same with p minus, taking common factor p minus. I rearrange all terms, and I get now the term next to p plus, right, is beta up plus 1 minus beta uq, and the term next to p minus is 1 minus beta uq, 1 minus beta uq. And this together means that the utility of the mixed lottery, beta p plus 1 minus beta q, is equal to the weighted sum of these utilities, right? So beta of up plus 1 minus beta of uq, okay? So this shows that the linear mapping I constructed not only represents the preferences, okay, that are rational, but also are linear, okay? So what is missing? So I have shown that the representation has to be linear, but I'm missing the expected utility representation, right? So the expected utility representation requires me to break down the expectation into the Bernoulli utility and the probability, right? So linearity is not exactly that. And here we're gonna just invoke a result from math. So this part we just call a famous result in mathematics, which is called the Rietz representation. And this basically tells you that if you have a linear mapping, any linear mapping, it is always going to be representable as an inner product of two objects, right? The object that you are evaluating the mapping on, so P, inner product, an object in the dual space. In this case, is another vector, Euclidean space. So U is a vector here that you take the inner product with P. So can you recognize easily that this is expected utility? So if you go and check the sum, right? This sum, the expectation, is not other thing than an inner product, right? So it's entry by entry multiplication of the entries in U, the vector, times probabilities of the particular state space, so the entry of P, and then sum over all states, over all entries of the vector. So expected utility is nothing else than just an inner product. And then the Rietz representation theorem tells me that there exists such vector U that makes this numerically equivalent. So this Rietz theorem basically implies the existence of the Bernoulli utility function. Okay? Do you understand? So this proof is basically a very famous proof that tells you a lot of information. Basically, we have shown the difficult part, the sufficiency part. If your preference relation is transitive complete and on top is independent and mixture continuous, then you're going to get an expected utility representation. That means there exists a Bernoulli utility such that you can represent the preferences as this inner product of the Bernoulli utility, which is a vector, times the probability. So it's a linear mapping, okay? what is missing here, of course, is that we want to know whether there is some recoverability issues, so identification issues. And this is the final result I'm going to show, which is I'm not going to prove because it's trivial, is that take a U and a U prime, and both represent the same preferences. So remember in chapter 3, we show that any utility representation is unique up to monotone transformations, right? So take the Cobb-Douglas, for instance. If I take the log of the Cobb-Douglas, it still represents the same preferences. Now, I will ask you this. I can ask Tyler. So Tyler, can you hear me?
Yeah.
Okay. So if say I have a expected utility U that represents the preference relation here is expected utility. So if I take the log of the expected utility, will this log of the expected utility still represent the preferences the preference that I described?
I'm gonna guess yes.
No.
Or no, because it's linear.
Yeah, exactly. So
Yeah,
it doesn't
yeah,
preserve linearity, right?
Yeah.
So the difference, of course, with the chapter 3 is that in chapter 3, we just have completeness and transitive, right? So these are fully ordinal properties, and therefore any monotone transformation, applying a logarithm, exponentiation to the power of 2, taking the root square, all of them, give you the same preferences. They don't modify what I'm doing. Expected utility is different. Expected utility is cardinal. It's not only ordinal. When you have this independence axiom, it makes basically the utility cardinal. So this is, of course, showcased in this theorem 13. So take the utility and then take U prime. Both are the same representations of the same preferences. Now, it actually happens that they both have to be related by a constant alpha, which is positive, and a constant V, such that U prime is equal to alpha of UP plus beta, okay? Plus V. So that means that here utility is almost cardinal up to 2 location. This is called a scalar location. Basically, if you normalize a scalar location, then you get unique cardinal representation. So you actually will get a number. You will get a util, okay? So remember the origins of utility. So who was told about Jeremy Bentham? So who knows who Jeremy Bentham is? Nobody? Really? You never heard of Jeremy Bentham? Okay. So Jeremy Bentham, if you Google it, right, Wikipedia, he's the guy that invented utilitarianism, right? So philosopher that now he is actually lives in UCL in the econ department. He went to a process of taxidermy and he lives in a shelf, right? So his idea is that his philosophy was that the objective of government and humanity is to increase the utility, right, the felicity of the majority of people. So he was thinking that we can actually measure how happy you are by consuming or having some service, in this case, a lottery, right? And then we know actually a physical number that can be measured as a physical unit. And then given that we know exactly how much happy something makes you, then the objective of the government is to compute that and then maximize that, right? So of course, he also thought that, everything has to be useful. So he also thought that if you die, then your body has to be used for something good. So he asked his body to be taxidermed and then put it in the shelf, right? To actually now serve as almost a monument or whatever. So, he lived in his dream and in his philosophy, and also he died on that. So yeah, no, and then of course, that was the basis of studying utility maximization and trying to understand utility. But of course, like the revolution in econ was to understand that preferences are hard to measure as a number, but we can still describe the ordinal content of preferences, right? I can ask you to run something is better than something, but it's more difficult for me to elicit the value that you give to this object versus this other object. Now, but for expected utility, it's very special because expected utility goes back to Bentham. Basically, up to normalization, I can know the intensity of preferences. So let's go back to this proof. So I declare the best lottery to be P plus. So I declare it to be utility equal to 1. And then P minus is utility equal to 0. So then what will be the values of alpha and B if for this particular information I'm giving you? So if P plus, the utility of that for all utilities possible, is equal to 1, and the utility of P minus is equal to 0 always, what will be the values of alpha and B that are compatible with that? So can Yoshiki tell me? Yoshiki, can you hear me?
Yes, sorry, I didn't get your question. Could you repeat your question?
Yes. So I'm telling you the following. So you have the following information. So the utility of P plus, which is the best lottery possible, is equal to 1. The utility of P minus is equal to 0 always, okay? So then, as in the theorem, take two utilities that represent the same preferences, U and U prime, okay? Now, what will be the values of alpha and B, right? Such that these utilities represent the preferences and they satisfy the information I gave you. So do you recognize that this question is about a system of linear equations?
What? Not really.
So the only way, right, this can happen for all utilities is if alpha is equal to 1 and B is equal to 0, right?
Yes.
Okay. So imagine, to do it by contradiction, right? Imagine B is not 0, right? Then the utility of P plus for some U will be 1, and then for another one will be, even taking alpha as 1 now, it will be 1 plus B, right? So that means it's not 1. So it's breaking my assumption, okay? So contradiction. Imagine alpha is not 1, you know, the same thing. You will reach a contradiction. The same for 0. My point being that, so if you want to actually have exact numbers of intensity, so thanks Yoshiki, right, of the utility, you just need to normalize the utility of the best alternative and of the worst alternative. So in my case, I'm normalizing U of P plus to be 1 and U of P minus to be 0. If I do that, then I can actually get utils. So if I run this experiment I described in the proof of the expected utility for two of you, say Eduardo and Yoshiki, and I give them this lottery, the lottery half $10, $0, sorry, 50% $10, 50% $0, and I elicit their utilities using this technique, right? I will get comparable util numbers, right? So Eduardo will have one intensity for P and Yoshiki will have another intensity for P, okay? So actually I can measure the intensity of preferences. Got it? So I want you to notice that expected utility is not only a model that is tractable, nice, separable, you know, easy to use. That's why people use it in game theory. I told you that the last class, but also gives you cardinality, okay? Gives you cardinality, which is a big deal. And that's why a lot of people use it for welfare analysis, okay?
Sorry for interruption. I just wanted to make sure if I heard it correct earlier. Did you say this utility can only be positive? I don't know if I heard it right.
The utility can only be positive? No. The alpha is the only thing that has to be positive, right?
Oh, alpha. Okay, sorry. I think I heard it wrong.
Because if it's not positive, then it won't be a monotone transformation, right? So then
okay.
it will break the transitivity.
Oh, okay. I guess I heard it wrong earlier. All right, thank you.
Okay. Yeah, but if I normalize, so what I'm saying is that, so this is not precisely cardinal because you have 2 degrees of freedom, right? So location and scale. But if you find a way to credibly normalize alpha and B, like versus requiring that the best lottery is 1 and the worst lottery is 0, then you can compare among people, okay? So I'm not saying you should do it. I'm saying people do it and they have good reasons to, because when you have expected utility structure, there is a lot more information you can elicit, and actually you have intensity of preferences. Okay, so my message for you is that even so, in the main setup, we are basically restricted to get ordinal information. If we add additional properties, like for instance linearity here, we can get actually cardinality back up to location and scale. Okay, so cardinality is not something that actually theories, they will never talk about cardinal objects, right? They say, okay, this is done, and we only talk about ordinal objects. But in real life, applied people are talking about cardinality all the time. Okay. In fact, if you don't have cardinality, you cannot talk about inequality, for instance. Okay. So cardinality, why you cannot talk about inequality? Because inequality discussions require that you have some intuition about how a dollar given to someone in some part of the income distribution has more impact on your welfare than giving the same dollar to someone in the lower part of the distribution. So it's actually an interpersonal comparison. The only way you can do this interpersonal comparisons is if you have some units, right? So there is no way you can talk about inequality, for instance, and redistribution without cardinality, okay? So cardinality is not impossible, but it's very hard. But expected utility is a case where if people were in fact expected utility maximizers, this is a testable condition, independence, then you can actually do cardinal comparisons, okay? Now the real question is, are people expected utility maximizers? And that's a different question, right? So, but yeah, cardinality is a very complex object. So cardinal versus ordinal is an ongoing discussion. I'm just telling you, don't give up on cardinality, but you actually need more assumptions or more data, right? If you want to do cardinal stuff.
Excuse me, Professor.
Sure.
So this theorem 13, this is basically telling us that the von Neumann-Morgenstern utility function is that they're unique up to positive, affine, or linear transformations.
Yeah, or location or scale. Yeah, it's the same thing. So many ways to say the same object, right? So positive affine transformations will still, preserve this finite structure that we showed before, and also, this means that basically up to 2 parameters, if you normalize 2 lotteries and their utilities, you can get actual utilities, right? So things that you can compare among individuals. Okay, everyone's on the same page. So this, of course, is a way stronger theorem that in comparison with chapter 3, right? Where any monotone transformation will still give you the same preferences. Okay, because of linearity, expected utility. So everyone is on the same page. Okay. So now let's study attitudes towards risk. So once we have understood, this particular model, we can now start understanding what to do with the model. And one of the main uses of the model is to try to use it to understand, model, and measure attitudes towards risk. So the idea is that maybe using expected utility, I can start modeling whether an individual likes to take risk or tries to avoid risk, right? So, and we call these attitudes towards risk. So now, for instance, imagine a subject that likes to gamble, right? Versus a subject that hates to gamble. So now, how can I model within the expected utility framework these 2 different behaviors? So the answer is going to be simply that the Bernoulli utility is going to have different shapes. So when you are risk averse, you hate gambling, then this utility is going to be concave, the Bernoulli one. And if you love to gamble, then the utility is going to be convex. And if you are risk neutral, then the utility is going to be just linear, okay? The Bernoulli. And so now, but what about models that are not expected utilities? So is there a way to understand attitudes towards risk a little bit more generally? And then how to understand this within the context of expected utility? So this is a little bit the role of this section of 7.6. So let's define first the general lottery, delta of Z bar that gives you with probability 1, the monetary price Z bar. And Z bar happens to be exactly the expectation of P. So take basically a P lottery, compute the expected value of this lottery, and then create a lottery that gives you with probability 1 the expected value. Okay? And then I'm gonna say that the decision maker is risk averter, so hates to gamble, if for any expected utility uncertain equivalent of P basically, with set equal to bar, it happens that this guy prefers the certain outcome of the average to the lottery itself. Okay? So this is the key information I want you to understand. So what does it mean? So I'm giving you with probability 1 the expected value of the lottery P. And then you can actually get lottery P. And this guy prefers the certain outcome with expected value than the lottery itself. Okay? So that means that this guy hates risk, right? Because if this person actually took P, right, you know that expectation is actually Z. So imagine the situation where you are expected utility maximizing, expected utility guy. And then what will be your utility if you are thinking of the expectation? Well, it will be exactly Z prime. So you will be indifferent, right? So this preference relation has the strict part, right? So is weakly better than P. It means that this also allows for individuals that actually prefer to get the expected value because there is some curvature on the Bernoulli utility that is making this smaller, right? So again, under the expected utility world, it will mean that if you're risk averter, if the Bernoulli is convex, okay? But for general models, you can understand who is risk averter by offering this person this certain lottery that corresponds to the expected value and comparing it to the lottery itself. So again, this is a little bit the opposite. So expected utility consumer is risk averter. And of course, it's concave, not convex. Is you hate risk if U is concave, right? So why? So this follows from something that is very known in probability statistics. It's called the Jensen's inequality, right? So have you checked that with Nael yet? So the Jensen's inequality is just this property that if you take the expectation of U, right, and you compare it with the U of the expectation, then if U is concave, the inequality will tell you will go in this direction. And if U is convex, then you have the other inequality in the other direction. So that means that the utility of the expected value, right, is above the expectation of the utility. So in other words, you will prefer the certain object, delta Z, over the P. In this case, you know, we're using, let me write also the dependence on the space. Okay? Everyone understands what's going on here. So this is a simple consequence of Jensen's, and it tells you the definition of risk aversion, and then it is specialized for the expected utility. So for expected utility, the nice thing about expected utility is you can capture the attitudes towards risk just by modeling the shape of the U. Okay? So if you're concave, now you are risk averted. Okay? Now,
Sorry, so the delta Z is just the type of lottery. It's another kind of lottery. Is that correct?
delta Z, by definition, right, is
Yeah.
a lottery that gives you with probability 1
Mhm.
the expected value. Okay.
Okay.
The general lottery.
Hello, Professor. So do you think the for a specific individual, would he change in his risk attitude? So for example, if I have 2 lotteries, so in lottery 1, so that is $10,000 in total, and I have a 90% chance to get all of them, and a 10% chance to get none of them. So the expected value would be 9,000. And in another case, I have for sure I would get 9,000. In this case, probably I will take more risk. So this is in my behavior in lottery 1, and in lottery 2, I have like 50 chance to get 5,000 and 50 chance to get 0, and the expected value. But in my second lottery, I will become more risk avert. I'm not sure if I have described my.
Yeah. So in this model, the U that captures your attitudes towards risk, right, remains the same. Now, there are different ways to model risk. So there is this, for instance, CARA, which is CARA, CRA, so constant relative risk aversion, right? So this will tell you that relative risk aversion will remain the same. A constant absolute risk aversion, CARA, will tell you that the absolute risk aversion remains constant. So different models give you different ways how people face risk. Now, but what they were saying, I guess, was a little bit to something that is called reference dependence. So, which is a model that allows you to have different utilities according to where you are in the space of lotteries. So U changes. And this is a model of behavioral econ. But right now, so again, so at this stage, we are just being with a very generic view. So I'm not specifying whether the relative risk aversion is constant or the absolute risk aversion is constant. In fact, they may not be. But I think what you're asking is a little bit more complex, which is that U changes in the space of lotteries, right? So as you go to certain part of the space, choice space, you instead of having U, you have B. If that's what I'm getting. Is that correct?
Yes.
Okay. Yeah, that's called reference dependence. And we're not going to study this in this class, but it's an important model of behavioral econ. So it's just to summarize for the rest of you. So, of course, one issue in this kind of modeling of risk is that this assumes that it's the same Bernoulli utility always, right? But it might not be the case. It might be that certain objects, like very extreme objects, right, you have a different risk attitude, right? So events on the tails that are, people have, they process differently in their brains than events in the middle, right? That's one particular way. The way that the behavioral guys do it is by thinking of losses versus gains. So for instance, imagine that in my monetary payoffs, I also have losses. So now you will have kind of a Bernoulli utility for losses and a Bernoulli utility for gains, and it changes, right? But so today I'm not going to talk about that. So we're talking about this model where U is always the same, right? U is a function, but it's the same for all the choice space. Okay, so this part here, I'm just gonna ask you to read. So definition 45 and proposition 21. So these are different ways that you can understand risk aversion, and they may be useful when you study something in macro or in finance. For me, I'm not gonna use them really, and they are just definitions. So it's just a definition I want you to read. So today I want to spend a little bit more time on trying to see the extension to reveal preference relations, right? To reveal preference and appear like and testing. So we're gonna do this at the end of the class. So I'm trying to reach faster that part. And so also break in 5 minutes. So let's finish this part and then we go to the break. So expected utility for infinite sets. So right now we just did for the case that the monetary outcomes space set is finite. Now I'm going to study the case where set can be infinite. So in particular, now I need to do more work, okay? So imagine Z be a set of prices, and now, you know, because this may be infinite, if I want to study the probabilities on it, I have to actually impose some structure to the set. So now we're gonna say that the collection of subset sigma on this power set is a sigma algebra. So I can just put probabilities over that. So did you get this with Nail already or no? Okay. So why do I use the sigma algebra? Well, I want to have probabilities on it, right? So I cannot put probabilities on power sets. So we know this is an impossibility. There is no sigma additivity. So I need this sigma algebra. So I'm not studying the whole power set because there are things that you cannot put probabilities on it. So the sigma algebra structure will be just a collection of subsets of the power set that I can put probabilities on. So the property of this collection of subsets of the power set is that first I have to have the empty set belongs to the sigma algebra. And then if an event E belongs to the sigma algebra, then also the complement belongs to the sigma algebra. And the more important property is that if I have a countable collection of events, AN, and all of AN belongs to the sigma algebra, then the countable union of these events still belongs to the sigma algebra, okay? And then we have this structure set, which is set with a structure of subsets, which is called the sigma algebra. Sigma, capital sigma, is a measurable space. basically I can create probabilities that now maps from the signal algebra to 0, 1. And I know that this is a probability measure if the probability of the whole set is equal to 1. And if basically if I take a probability of this union is equal to the sum, the countable sum over this. And this is one way to define it. Now we have this structure, which is now the set of probabilities over this space z comma sigma. And for sure, we're going to simplify it to the simplex over z. Okay, but there is a sigma algebra structure behind it that makes it measurable. So I still define the compounding lottery in this way. This is the same way as before. Notice that here I'm defining it instead of atoms, as in the discrete case, I'm defining this composition of compounding lotteries for events. So events E are sets of events, So these are potentially infinite sets. So now I have alpha P plus 1 minus alpha Q of the event E is equal to alpha probability of event E plus 1 minus alpha Q probability Q of event E. Okay. So in the infinite space, I also need to establish some topology to define continuity. Okay, and one famous topology that is very useful in this world is what is called the weak star topology, which basically means that I'm going to say that Pn converges in the weak star topology to P, even only if for every continuous and bounded function f, if I take the integral of f with respect to the measure dPn. Then basically this number, which is already an integrated object, will converge to the integral of the f p. So it's the same f, so it's a testing function. And then I check whether the integral of the measure Pn goes to the value of this integral f dp. And the key here is that it's weak star topology because it will this will converge for every continuous and bounded function f. Okay, but it doesn't need to converge for all functions. They have to be continuous and bounded. Okay. So under the weak star topology, we say that for any P, the sets Q that are the upper contour set basically of P and the lower contour set of P are open in the weak star topology. Okay. And again, this means that the set with the weak preference relation, the weak upper contour set that includes the indifference and the lower contour set that includes the indifference are closed in the topology. Okay, so this definition is even closer to chapter 3. So if I take Pn and Qn, and Pn and Qn are weakly preferred to each other for all n, and then I take under the weak star topology that Pn converges to P and Qn converges to Q, it has to be that in the limit P is still better than Q, okay? So this again is ruling out this kind of lexicographic behavior and so on. So it's the same object, just that because it's the space of lotteries, we have to define topology differently. So as opposed to the space of commodities, right? So now the theorem says a preference relation that is of course rational. So let me write it in here. That satisfies independence and weak star continuity, even only if there exists a U that is bounded and continuous such that the expected utility of P is equal now to the integral, right, of uz with a measure dpz, okay? So this is extending our result to the case of infinite outcomes. So now lotteries can be, for instance, a normal distribution, so it can be Gaussians, they can be chi-squares, whatever, right? Previously, we're just dealing with finite distributions. Now we have, potentially infinite ones. The proof turns out to be actually the same because you can use still this calibration theorem from before. So the lemma that gives you linearity is the same. Then, of course, you have to use now weak star continuity, but the proof is the same essentially. And the Rietz theorem will still give you this representation. Okay. So the Rietz theorem works even for these more complex spaces. Okay, so you have to apply the Rietz theorem for the general spaces that we're dealing here, and we're going to get still this is an inner product on a more complex space. Okay, it's an infinite inner product, but still is an inner product. Okay, so the theorem actually the proof is the same. So of course I did it for the simple case, and this is the more general case. Now, here important caveat for how to study this part. So I did the proof for the finite case. So I may ask you to do some modification of that for some model that changes a bit. Yeah, possibly. Will I ask you to do the very hard problem with weak continuity and prove it for the infinite case? Not really. That kind of, so I'm not going to test you on how to prove theorem 14, but I can ask you to do some modification of theorem 30, the previous theorem, 12. So why not the technical part? Obviously, is beyond the scope of this class. This is more a decision theory class, right? So in my own decision theory class, I was playing with this thing and proving the theorem for different complexity of spaces, okay? So this is a specialized field knowledge. I want you to understand the logic, which is the theorem 12. Got it? Okay, any questions? So when I'm doing this infinite sets case, because in the end, a lot of applications require infinite distributions. For instance, if you're doing for finance, usually assets are described with returns that have continuous returns, right? So for instance, you say, this asset has returns that are distributed with a Gaussian, okay? So that is covered by this theorem 14, not by the previous theorem, okay? So a lot of the applications that we do require infinite dimensions, okay? That's why I introduced it.
A
So
question, Professor.
Yeah, go ahead.
Because you define the sigma algebra and use a countable set, but then you define the UP use integral. So I'm a little bit confused about this part.
Can you say that again? So I defined the sigma algebra. This is a standard thing of
It's
sigma.
a countable. The AN is a countable collection.
Yeah. So this is just a property, right? So because this is a countable collection, I can have this sum, and then I have to define this integral, and I can use the weak start continuity, right, to define pretty much an integral using sequence. So yeah, there are many ways I can define an integral in this way, but the property I require is just that in this countable union I have this summation, right? This is a property, but I didn't define integral, so I'm not doing a probability class, right? So the integral is defined in this space, and that's what I'm using, right? But one way to have the intuition is that I can use pretty much limits of this construct one integral. Another is the Lebesgue integral. So there are many ways to do it, right? With simple random variables, take limits. But that's a probability class. So I'm not going to do that. So if your question was, I didn't define integral, yes, I didn't, right? But this is the property I need. It's just the countable union has to be additively separable. Okay.
Thank you.
Okay. So yeah, so there are, so this is our representation. And again, we haven't proved that, but it's, again, the logic is very simple. The Riedt representation theorem will do the heavy work for us if you need to prove it. Okay. So here there's a part of the Mas-Colell reading that is called demand for a risky asset. And usually I did it in class, but now I'm going to send it as a problem set. So this is going to show you basically an application telling you that even if you are risk averter, you can still demand positive quantities of a risky asset, right? And basically tells you why, and the proof uses first order conditions and so on. It's not very illustrative, so I'm going to send you a problem set that has more a parametric problem plus this problem, and then you can practice what we learned today. So right now we're going to take a break of 5 minutes. So yeah, so see you at 2:08. Hi guys. So everyone can hear me?
Yes.
Okay. So yeah, so the previous class I also told you about the first order stochastic dominance relation. So this part I already told you. So we can add this notion of monotonicity to our respective utility. So we can compare two random variables. And in particular, we can compare them by the cumulative distribution. So if you have two distributions such that f is the cumulative distribution for any x is always less than or equal than g, then it happens that the u of f has to be greater than or equal than u of g. So one of the options is going to always give you better outcome. So the easiest way to visualize it is for discrete case, right? You have a vector. So remember, these are probabilities, but roughly what it means is that entry by entry, you have a higher probability on every outcome, right? So because these are added to 1, then you have to think of the cumulative. But this is kind of the analogous notion of monotonicity in the commodity bundle space. So more is better, right? So here you want, of course, if you are comparing two distributions and one is giving you always better outcomes, first order stochastic dominant, then you will pick that. So that's a reasonable thing to ask. Now, the expected utility doesn't have to be first order stochastic dominant, but it is whenever you have whenever you require the Bernoulli to be strictly increasing. Okay. So if the Bernoulli is strictly increasing, then you satisfy first order stochastic dominance. Else, the first order stochastic dominance, of course, is a partial order, so it doesn't imply expected utility. But your expected utility can respect first order stochastic dominance. So why this is a big deal and why they actually stuck in Mascolel and others is that not every model of risk that people have proposed respects the first order stochastic dominance. And that seems to be an issue. So from the point of view of decision theory in the traditional way, a lot of people say, if you have a sane model of behavior under risk, you will want the model to at least respect first order stochastic dominance. So if something is obviously better, your model should predict that it's peak, okay? Now, what do you think about that? Do you think that's a good thing to ask? Do you think humans satisfy the first order stochastic dominance? So maybe Fateme, that's the correct pronunciation. Can you hear me?
Could you please repeat your question?
Yeah, so I was saying that one of the kind of virtues of expected utility is that when you assume that the Bernoulli utility is strictly increasing, then expected utility satisfies first order stochastic dominance, in the sense that if f is first order stochastic dominates g, then the utility of f is greater than or equal to the utility of g according to expected utility. So my claim is if you have a model that doesn't respect expected utility, doesn't respect first order stochastic dominance, do you think it's a bad model of behavior? In other words, do you think humans satisfy first order stochastic dominance?
I'm actually not sure, but I think it's just an option to have for your model. So I think there are models where we don't have this expected utility, but they might not be rational, I think. But
Well,
like human behavior is not always rational.
Yeah, but there's two different things, right? So you can see here there are many layers. So first order stochastic dominance is just a transitive relation that is not complete. So first order stochastic dominance is not implying rationality, right? So you can have models that are not complete that still satisfy first order stochastic dominance. Now, expected utility happens to be complete and transitive and also respect first order stochastic dominance, okay? So now the question is really, how we think about decision theory. So it's a methodological question. So if you really thought about my claim, what I'm doing is a normative claim, okay? So I'm saying basically humans should do this, okay? Should. So I'm telling you, look, if you're smart, then obviously you should pick first order stochastic dominant objects. Do you agree? But that's a normative stem. So here is where people get confused. So when people teach or learn expected utility, they don't fully separate the two dimensions to this model. So historically, this model has two justifications. The first one is normative, right? And the second one is positive. So basically you say, this model could describe behavior well, positive, because description. And normative is, this model is what you should do if you're smart, okay? So normative statement. So all decision theory was normative in the sense that people said, okay, we don't have data, okay? So we're philosophers of decision making. So how do we model decision making? So we model consumers that are ideal in a way. It's how you should behave, okay? Do you understand? So the origins of decision theory were philosophical origins. So they were normative. So you were saying, oh, look, people should think in an expected utility way because, for instance, expected utility respects a sanity check, which is the first order stochastic dominance relation. So if F is first order stochastic dominant to G, then expected utility with a strict increase in U, so you like more money to less, respects this sanity check pass, okay? Now, if you are modern and expected utility is a scientific theory, then I cannot tell consumers how to behave, right? It's more an empirical question. So do people in real life satisfy first order stochastic dominance? No, they don't do it, okay? And again, so this is actually kind of interesting because in fact, if they are smart, they should respect first order stochastic dominance. So important example, you will tell me, yeah, maybe they fail in some silly experiments. But in real life, there is a lot of evidence that when people buy insurance, there are insurance contracts, right? That always give you weather in every state of the world, okay? Are weather in every possible dimension and cost the same. And people choose dominated options, okay? So they choose worse insurance contracts that are available to them. So why do you think people do that? Who can tell me a justification of why people may not choose the optimal contract?
They don't truly understand how to rank the contracts.
Perfect, right? They understand it's complex, right? Complexity. Where is complexity in this model? It's absent, right? Attention, complexity, you know. And so most people don't understand the contracts, how they can choose the best thing. They don't even know what is the best thing. Another reason is just lack of awareness, okay? So you see on the TV that there is this insurance, right? Travelers or whatever, or TV. Or what most people do is they don't like to think even on insurance, right? So you call you talk to someone at the university, you talk to someone and say, okay, you live already in London, tell me what insurance should I get, okay? So if someone already did something that was suboptimal, you're gonna do also a suboptimal thing, right? Who has spent among you, if you're trying to get insurance or something, like for instance, renter's insurance, which I suggest you do. Who among you actually did research about that? So if you got a car, you had to get car insurance. Did you research? How much time did you spend on it? Well, you're a PhD student. Some of you actually will do even, you know, a spreadsheet, but some of you don't, right? And so this is the question, right? Even, you know, people like you won't spend that much time. Imagine the average Joe, right? So that's the issue. So real life is more complex. And again, I want you to understand that, for instance, these claims in Mascolel about first order stochastic dominance and so on, they are just claims that are normative. So you have to really be try to separate normative statements from positive statements. So in short, so first order stochastic dominance is kind of an interesting property to have, and it's kind of a intelligence test, if you want, right? Optimality test, but it's not something that people actually can do and will do. In fact, they don't. So therefore, the fact that first stochastic dominance respects expected utility, you know, it meant a lot in the time of Mascolel. We don't care as much, but it's interesting at least that this model can do that. Now, there are models that if you for instance, reference dependence models and probability weighting models, which are models in behavioral econ. If these models usually predict that you always break first order stochastic dominance. That's kind of the other extreme. So this allowing smart guys, okay, at all. So that's also a bad thing to have, right? So in that sense, those models are not great. So you have to fix them, and people have worked on that. So now I'm going to tell you something, a Alais paradox. So I have to tell you because historically it's very important. And the Alais paradox was a thought experiment, right? By Alais that said, look, the expected utility is kind of nice and you philosophers love it, but I'm gonna give you a thought experiment that will blow your minds and tell you expected utility is bad. So it's not data, it's not a real behavior, but it's something that in his mind is reasonable. However, even being reasonable is not expected utility. Okay, and he called it a paradox. So it's good at sales, right? But it's not really a violation of expected utility because it's not real data. Now, lucky for Ale, when we run experiments, or modern people run experiments, and they found actually this kind of behavior in the data. So therefore, this is violations of expected utility. So we now found evidence against expected utility. Okay. So I'm going to tell you the Ale paradox, but it's nice to see how can we, with a simple experiment, we can see violations of independence. Okay, that's the thing I want you to learn. So imagine you have set with only 3 prices, and you have 2.5 million, 0.5 million, and 0. And then I create 2 choice sets, 2 experiments. In the first experiment, I make you choose between a binary comparison, L1 lottery versus L1 prime lottery. The first lottery gives you, with probability 1, 500,000. And the other lottery is more complex, right? It gives you, with 10%, 2.5 million, 85%, 500,000, and 0.01, 0. Okay, so among you, can Faye, do you hear me, Faye?
Yes.
Which lottery do you prefer, L1 or L1 prime?
L1 prime.
So, okay, so Faye likes L1 prime, right? So let's, now, Eduardo, can you tell me which lottery do you prefer?
I also prefer L1 prime.
Is there anyone among you that likes L1?
Is the third price is 0?
Sorry?
The third price is 0?
Yeah.
I prefer L1 then.
Okay, so that was Zach.
Nico.
Nico, okay. Okay, good. Now, so now the second lottery, second experiment is L2, gives you 11%, 500,000, 89%, 0, right? And this compares it to now L2 prime, which is 10% of the big prize, right? 2.5 million and 90% of nothing, okay? So now the same, so Faye, which one do you like now?
L2 prime.
Okay. Eduardo?
Same.
Nico?
L2 prime.
Okay. So now, some individuals like Nico, right, like L1 over L1 prime and L2 prime over L2, okay? So I just found out that Nico is not expected utility maximizer. And then we're gonna think about Eduardo, right? And Faye. But for Nico, why he cannot be expected utility maximizer? Well, if L1 is better than L1 prime, then it has to be that the utility of 500,000 with probability 1, right, is greater than the expected utility of the other lottery, right, which this weights. So 0.10, 2.5 million, 0.89, 0.5 is 0.01, is 0. And then if I take and do just an algebraic operation, add and subtract from both sides of the inequality 0.88 u of nothing minus 0.89 of 0.5. So notice why I'm doing this, because notice that I have this quantity here for the 500,000 and also I have nothing here with 0.8, right? So by doing so, I just rearrange terms and then we get the following quantity. So I get that 0.11, right, of 0.5, which is 1 minus this quantity here, right? So I get 0.11 of 0.5. And then I get the part that I was adding, 0.89 of u0, u0. And then from the other side, I do the same. So I get 0.1 of 2.5 million plus 0.9 of u0. So this tells me, this implies that L2 has to be better than L2 prime, okay, according to expected utility. So notice that in this derivation, I didn't have to tell you the value that you assigned to gaining 2.5 million, right? So this is completely non-parametric. However, just due to the linearity, if you prefer L1 to L1 prime, then if you're expected utility maximizer, L2 is better than L2 prime. Okay, so Nico is not expected utility maximizer. Okay, now you can do the computations for Fea and Eduardo. So in particular, I think they can be compatible with expected utility maximizers, but you know, right now the important thing is to understand you know, what happened with expected utility, right? So Nico, can you tell me why you prefer the first? So just give us a reason. Why do you like L1 to L1 prime, and why do you like then L2 prime to L2?
Because for me, like the 2.5 million versus 500,000, the benefit from that isn't as much as the benefit from going to 0 to 500,000. So I would rather have no chance of getting $0 because 500,000 would give me, like, I guess in utility would make me a lot happier than going from 0 to 500,000 than from 500,000 to 2.5 million.
Yeah.
So I guess I'm risk averse.
Yeah, but it's more than that, right? So you see that it's really, remember that this expected utility world was kind of being full substitutes across the states. So, but for instance, Nico is describing us that he actually has particular feelings about each state of the world, right? So I versus really dislike of losing, right? So if you do that, then actually some states are more important than others, which goes against the idea of perfect substitutes, right? So in a way, you know, you cannot be expected utility if you have that kind of utility. So is Nico wrong? No, right? That's the key thing. So at the time of Ale was saying, look, this is perfectly reasonable, right? However, it's not expected utility. So boom, expected utility is bad. And they start discussing, right? That was all decision theory. You can see it was cool, but lame if you think about it in current terms. So I need to run an experiment, right? Why should I say Ale has these preferences and therefore expected utility is bad? You know, doesn't follow. It's not a paradox either. Formally, it's not a paradox. But the interesting thing is that if I give these choices to people like Nico, and then I run it many times, then some people actually fail it, which is not surprising, right? Because not everyone has to satisfy the independence axiom. So in particular, Nico could also tell me, I don't follow the independence axiom. No, just kidding. But you know, what it means basically is that your preferences, Nico's preferences, do not satisfy independence. Okay.
Quick question about this. I'm not sure, but have there been any experiments where they say like certain portion of people fail this independence?
Yeah. So I'm gonna send you a link in Slack that is about testing axioms, right? And you know, you find a significant fraction. I don't remember exactly the names, but usually most people fail the expected utility axiom. Okay, so the independence axiom. But they will fail more often whenever you have these extreme prices, right? Like in this case. So as Nico was saying, it has something to do when you have these extreme values, then people start giving some particular meaning at winning or losing 2.5 millions versus 0, right? Okay, so, okay, but beyond that, I want to go back and, you know, and think that this is not surprising because basically you have a model that is fully linear, right? It's the simplest model possible, right? So why in the world should people be like that? You know, it's very unlikely. And in fact, it is. So then the next thing I'm going to tell you is that most people use this model. Why? So, well, first reason is because it's tractable. It's nice and easy, mathematically easy to work with. So if you're dealing with something complex, like strategic interactions in a game that is super complex, then you want to use the simpler model of decision, right, to derive something. If you're doing finance, which is also very complex, then you want to use, again, the simplest model possible, okay? And gives you cardinality. So tractability has been the reason why people use it. But there is kind of a deeper justification, and it's the following. So imagine you have some preferences among risk, and they can be whatever, right? Very hard to describe. Then, you know, one way people model stuff is by taking a linear approximation. Do you agree? So as long as you're smooth, you can do a Taylor approximation around a point. So imagine you are studying how people choose among lotteries that are very close to each other, right? So not extreme events. And so therefore, expected utility cannot be that bad because you can always approximate linearly, locally, and everything, right? So that's kind of the justification of why this model still is used. But remember, so if you use this model, it has to be local in the sense that the probabilities you are using are not too far away. Okay, so I'm going to tell you now the reveal preference part and an experiment. So now consider the problem of maximizing. We're going to put together this chapter with the chapter of consumer maximization. So this is similar to the experiment. So you're maximizing now expected utility across the states. And now the goods are contracts that give you money for each state of the world. So now the commodity bundles is a vector X that pays monetary quantity XS in a state S. So you're maximizing the expected utility of this contract, an insurance contract, for instance, subject to what? That the price of each state, so this contract has state contingent pricing, will be equal to an income level. So your contract tells you that if you suffer an accident, you pay this co-payment, right? But if you don't suffer this, you pay a prime, right? You pay the usual money you pay to the insurance. And then, these prices are conditional on the state. This is PS. And you multiply it by the money you obtain on each state, and this is equal to the total income. So this is the problem. And now assume that U is concave. So you have only risk averse agents. And now what will be the optimal portfolio or contract that you buy here? Will satisfy first order conditions, right? So this is the probability of a state S multiplied by the U is here a cardinal utility. So it's U prime X of S is equal to lambda PS. So again, so if this is a vector, right, this would be nabla. So in the generic case, right? So this is a vector and so on. But if you're thinking of a state, so just a monetary price, then this remembers a scalar. So we have this. So now we can also so this is the object here. And now imagine you have a data set, right, of prices and consumption. These consumption now are arrow securities. And now we say a data set is rationalized by expected utility maximization whenever there is expected utility that is always XTS, the data, is always better in utility according to these probabilities than U of YS, such that Y is always affordable. And in particular, turns out that I can actually test this very easily by running a simple reveal preference test, which tells you that there are numbers, beta, such that the following first order condition inequality works. So pi S, the probability of state S, beta S of the observation T divided by PST is equal to pi S prime equal to beta S prime T divided by PST. So this is just back to the first order conditions. And remember that if I divide two states of the world, right, they have to be equal because the prices are the same. So the lambdas disappear, and then you rearrange these terms. They are PS prime divided by PS, and then you have here pi S divided by pi S multiplied by VS prime divided by VS. So this is just marginal rate of substitution equal to relative ratio of prices weighted by the probabilities. And the proof basically follows from the first order conditions. We derive the following first order condition as before. Then we solve for lambda t. And then this implies, because lambda t doesn't depend on the state, you can equate these different lambdas and we obtain the condition before, okay? And this beta is just the marginal utility of xt for observation t. So it turns out that just by testing this system of equalities with numbers, beta, s, so you're just solving for betas, you can test whether a data set is compatible with expected utility maximization. So we go to the data set, this is the data set with two goods. We test GARP. We know the GARP fails in most cases. And basically without dropping anything, it's just 26%. This is this particular Carib 2007, so two goods only. So it's different from the one you're working on. And here you have expected utility, and you can see that only 4% of individuals pass, okay? So if you drop now one observation, 11% of people pass, 2 observations, 15, and 3 observations, 21%. Okay, so in general, expected utility seems to be really bad. Now, so I'm going to stop there, and you're free to go, and then the rest of the people can ask me questions. But my final comment is that expected utility is not a model that is great at describing behavior, but it turns out to be widely used basically because it's very tractable and nice. So a little bit, you know, the revolution in Econ is that as we are trying to take our models to data, a lot of models stop working, right? And expected utility is the prime example. However, you know, finance is mostly done with this. Game theory is mostly done with this. And the reason is that the models are so complex that usually you have to use the simplest model possible to get something out of it. But at the same time, you know, realize that the majority of work, empirical work, is actually generalizing this expected utility, okay? In which directions? So there are 2 main directions. The one is reference dependence. So you have the realm of losses and gains. And the second is, of course, in attention and trying to understand, you know, how to model the complexity and so on.